One of the most important things about delta H and other thermodynamic functions that we will encounter is they are all state functions. That means that the change in delta H is independent of how you got there. Okay, so for example, when I come in the morning, I leave my home, I end up here. That is a thermodynamic statement. Now, did I drive? That's actually a kinetic statement. How fast did I get here? That's a kinetic statement. Which path did I take? That is a kinetic statement. Thermodynamic statements, state function, you start, you finish, all you care about is the distance between those. Okay? Now that also means that thermodynamic changes are reversible changes. And both of these lead to really important relationships. I'm just going to state here, and then we will illustrate by lots of examples in class. So let's just say a nice little reaction, A plus B goes to some substance C, and I'm going to tell you that that has delta H1. Well, because it's a reversible thing, going from A and B to C is delta H1, going from C back to A and B, it would be minus delta H1. And I hope that makes sense to you. Okay, because you start and you end, and all you care about is the difference between them. If going from the start to the end is one value, going from the end back to the start is minus that value. Also importantly, the path independent aspect. If we have another situation, C goes to D, and that is delta H2. Well, then when we put those together and we say, let's not go through C, let's go straight from A and B to D, well, then the overall delta H for this is just the sum of what the delta H was for the first part, going through C, delta H1, and then going from C to D, delta H2. Couple of really important relationships that we will expand upon with examples in class. Now, most of the time that you see the so-called Hess's law, which is what we just introduced, it's in a very specific form. And that's associated with a general chemical reaction. We think of it reactants going to products. And then if we just imagine breaking down those reactants to their elements, and then putting those elements together to make the products, okay? Because the reactants have got the same number of each type of atom as the products, we can think on paper, if instead of going straight from reactants to products, which would have a delta H of delta RH, and I'm introducing this notation here, just the generic for a reaction, delta H for the reaction, that R in between. Delta H for R is going from reactants to products. What I want to do is I want to break it down, go to the elements first, and then back to the products. Okay, now why do I do that? Well, because as we go from reactants to elements, we're effectively doing the reverse of the heat of formation. Remember, heat of formation of a substance is where you go from its elements to that substance. So we're going from the substance, which is a reactant, call it reactant 1, to its elements. And then we'll do the same for, say, reactant 2, where we have to break down reactant 2 to its elements, so that's the reverse of its heat of formation. And in general, going from the reactants to the elements, we'll have a heat change of where we sum up all those heats of formation of the reactants and put a minus sign on it, because instead of going from elements to reactants, we're going from reactants to elements. Same idea as we go from the elements to the products, but here, of course, it's not minus the heat of formation, it's the heat of formation itself. So to get product 1, it's going to be the heat of formation of product 1. To get product 2 from its elements, heat of formation of product 2. And overall, to go from the elements to the products, the heat change is going to be where we sum up all of the heats of formation of delta H of the products. Now, according to Hess's law, delta HR is where we go from reactants to products, but delta HR can also be associated with going from reactants to elements and then elements back to products. In other words, a very general result is that the heat of a reaction is where we sum up all of the heats of formation of the reactants and make those negative, all of the heats of formation of the products and keep those as positive, put them together, so heats of formation of products minus heats of formation of reactants. Again, we will do a lot of examples of these in class, plus of course there are lots in your quizzes. Delta H relationships, Hess's law, extremely important. In general, Delta H is a state function, a thermodynamic function. That means we can reverse it and change the sign. That means that we can take different paths, add them together to get the overall path, and add together the same delta H values of those paths to get the overall value, which in a specific sense means that for any reaction, we can add up the heats of formation of the reactants, add up the heats of formation of the products, subtract the reactants from the products, and get the heat of reaction.